All right. By the time we finish this section, we will be able to compute probabilities of compound events using the addition rules. And there are two addition rules that we're going to touch base with. All right, addition rule number one, ladies and gentlemen, assumes that events are mutually exclusive. Now, what does it mean for two or more events to be mutually exclusive? If two or more events are mutually exclusive, or sometimes we say disjoint, then we say that the events cannot occur simultaneously on any given trial of a probability experiment. Okay, so again, two or more events are mutually exclusive or disjoint if they cannot occur simultaneously on any given trial of an experiment. All right, if we have these two events, if event A is defined to be that a randomly chosen student is a woman versus event B is that a randomly chosen student is a junior, are these mutually exclusive events, or could they occur at the same time? The answer is they could occur at the same time because we could select a woman that's also a junior. So these are not mutually exclusive or disjoint events. Okay. How about these events? Suppose event A represents the event that a randomly chosen card is a 5, and event B is the event that a randomly chosen card is a jack. Could we, when we select a card from a deck, select both a 5 card and a jack card simultaneously? The answer is that's impossible. And so, ladies and gentlemen, these are called mutually exclusive events or disjoint events because they both cannot occur simultaneously on any given trial of reaching into a deck and selecting a card. All right. Now, if two events A and B are mutually exclusive or disjoint, which means that they cannot occur at the same time on any given trial of an experiment, then to compute the OR probability, the probability of event A or B occurring, we would simply add the individual probabilities together. It would be the sum of the probability of event A occurring and the probability of event B occurring. Okay, this again is assuming that events A and B are mutually exclusive or they are disjoint, which means they cannot both occur simultaneously on any given trial of an experiment. Diagrammatically speaking, if two events are mutually exclusive, then we would expect, if we use a Venn diagram to represent the probabilities of each event by these circles, these colored circles, that we would expect there to be no overlap between these events or these circles. That's to say that they're mutually exclusive using a Venn diagram. Okay. All right, now this is called addition rule number one. All right. If your events are mutually exclusive, then you're going to compute an OR probability by using this addition rule. We'll call this addition rule number one. Let's see if we can apply that rule to some examples. Suppose 15% of students in a class are freshmen and 22% of students in the class are sophomores. What is the probability that a randomly chosen student is either a freshman or a sophomore? The key word, the connective word that separates these two events is the word or. Because you see the word or here, Lena, we're trying to compute this or probability. You would be thinking of using an addition rule. Now, next week, when we see the word and separating two events, we will use some sort of a multiplication rule. All right. Now, being a freshman or being a sophomore are considered to be what? Mutually exclusive, because you cannot be both a freshman and a sophomore simultaneously. So those are mutually exclusive or disjoint events. So therefore, the probability of randomly selecting a freshman or a sophomore would be equal to the sum of the individual probabilities. So it's equal to the sum of the probability of selecting a freshman and the probability of selecting a sophomore. So that would be nothing more than 0.15 plus 0.22, which is 0.37. So there's a 37% chance that if we randomly select a student here among these classes, that we will select a freshman or a sophomore. All right, we use the first addition rule to compute that or probability, because again, it's assumed that these events are mutually exclusive or they are disjoint. All right, suppose 18% of students in a class have taken the class before. What is the probability that a randomly chosen student is a freshman or has taken the class before? All right. Well, being a freshman or taking the class a second time are not mutually exclusive. Perhaps let's assume that like it is a spring semester and the student first took the class in the fall. Because later on we could have somebody taking this class a second time that is also a freshman. All right. So these events are not mutually exclusive. They could occur simultaneously. And because they are not mutually exclusive or disjoint events, we cannot use the first addition rule to calculate this or probability. We're going to need another rule, another formula for doing this. Okay. So we now are ready to look at what's called the second rule for addition. This rule relaxes the requirement that the events be mutually exclusive, in the sense that if our events are not mutually exclusive, diagrammatically, that would be indicated by the fact that there is some sort of overlap between these two events, meaning there are common simple events or outcomes that belong to each of these events here. All right. Now, in computing the probability of event A or B occurring, if the events are not mutually exclusive, the deal is this. In order to compute the probability of event A occurring, we would have to count every element in the circle that represents the outcomes for event A. That includes counting the ones that are in the intersection here. And computing the probability of event B occurring, we would also have to count all of the outcomes in event B. That also includes those that are in the intersection. Well, in the intersection, we already counted all the outcomes that were in event A, and since they're also shared by event B, they were double counted. And because we cannot double count outcomes, we have to compensate by subtracting off the probability of the intersection of these two events occurring. Therefore, we run into what is called rule number 2 for addition. And this is the second addition rule right here. So if two events A and B are not mutually exclusive or disjoint, meaning they can both occur simultaneously on a given trial of an experiment, we would have to use this formula to compute the or probability. It would be the sum of the individual probabilities, but then we have to subtract off this and probability at the end. This and probability is the intersection portion. Again, that's necessary to account for the fact that we double counted the intersection outcomes twice. We double counted them. This last probability is sometimes called a joint probability, okay? A joint probability. So that's the second addition rule. Here's an example. There are in a standard deck of cards 4 jacks and also there are 52 cards, 13 hearts. What is the probability of drawing either a jack or a heart from a deck of cards? Well, To determine what addition rule we use, we need to determine if these events are mutually exclusive or not. Can both these events occur simultaneously when we draw a card from a deck? Can they occur at the same time?
Yes.
Yes, they could if we selected what card?
The Jack of Hearts.
The Jack of Hearts card. Okay. So these events are not mutually exclusive. And therefore, to compute this or probability, we're going to have to use the second addition rule. All right, so therefore, in order to compute the probability of selecting a jack or a heart, it's going to be equal to the probability of a jack being selected, which there are 4 jacks in a deck, so 4 out of 52 is its probability, added to the probability of selecting a heart. There's 13 hearts in a deck, so that's 13 over 52 for that probability. But to compute the probability of selecting a jack and a heart, we had to count the Jack of Hearts card not once, but twice. And because we double counted that one card, the Jack of Hearts card, we must compensate by subtracting off, namely the probability of selecting the Jack of Hearts card. And the probability of selecting the Jack of Hearts card would be 1 over 52. So therefore, the probability of selecting a Jack or a heart after we do the arithmetic would be 4 over 13 after you reduce this fraction. So there's about a 31% chance that if you reach into a randomized deck and select one card, you will select either a jack or a heart. So that's the illustration of using the second addition rule, where our events are not disjoint or they are not mutually exclusive. Okay. Okay. So it really comes down to, depending on, as to what rule we're going to use, whether we use the first addition rule or we use the second addition rule. It depends upon whether or not the events are or are not mutually exclusive or disjoint. That's what dictates what rule we're going to use here. Okay. All right. Any questions about any of these addition rules here? All right. Sometimes the second addition rule is called the general addition rule. The first one sometimes is coined as being a special addition rule. Okay. All right. Well, let's see if we can go now to our textbook and entertain some problems here. Okay, we'll go on down. All right, problem number 1. Define mutually exclusive events and give an example of 2 events that are mutually exclusive and 2 events that are not mutually exclusive. Okay, so what does it mean for events to be mutually exclusive? Anybody? What does it mean for 2 or more events to be mutually exclusive?
They can't happen simultaneously.
That's correct. They cannot, happen at the same time on any given trial of any probability experiment. All right. Can anybody give me an example of 2 events that are mutually exclusive events for a particular experiment? Let me throw this out there. How about if we roll a die, a fair die? What would be some events that could be defined on this experiment that would be mutually exclusive? Anybody? If we roll a fair die. Give me a couple of events surrounding this experiment that we could define to be mutually exclusive or disjoint.
Rolling 1 or a 2.
Okay. Yeah, event A could be that we roll a 1, and event B could be that we roll a 2. those events certainly are mutually exclusive, because when you roll a die, it's impossible to roll both a 1 and 2 simultaneously. Here's another example. Suppose we define event A to be that we roll an even face, and event B to be the event that we roll an odd face. Those would be mutually exclusive events. Okay. Can anybody give me an example of 2 events that are not mutually exclusive for maybe a particular experiment? Not mutually exclusive.
Pulling a red card and also a face card at the same time.
Yeah. Event A could be defined that we select a red card, and B be the event that we select a face card. And those events would not be mutually exclusive, because we could select, the Jack of Hearts or the Jack of Diamonds, and that's selecting a face card and a red card at the same time. Okay, so those are not mutually exclusive events. Suppose that I have an experiment. I go to a university and I randomly select a student from the university. Suppose that I want to compute the probability that this student is either a freshman or an engineering major. Are those 2 events mutually exclusive?
No.
No, because I could select a student that's both a freshman and also what? Majoring in engineering. So those events could occur at the same time. All right. That's possible. Here's another good example. Suppose that I define event A to be that it rains somewhere on planet Venus, and event B to be that it rains somewhere on planet Earth. Are those events mutually exclusive? If I wanted to compute the probability that it rains on Earth or on Venus, are they mutually exclusive events?
No.
No, because it could rain somewhere on Earth and Venus simultaneously, correct? Those are not mutually exclusive events. Okay. Now, are these mutually exclusive events? If I define event A to be that it rains tomorrow in Flint, and event B to be that it does not rain tomorrow in Flint, then the probability of event A or B occurring, would those be mutually exclusive events?
Yes.
Yes. And what kind of events are those? Listen again. Event A is that it rains in Flint tomorrow. Event B is defined to be the event that it does not rain in Flint tomorrow. We call those what kind of events? Do you remember?
Complementary events.
Those are complementary events. So we're learning very quickly here that an event and its complementary event are always what? Mutually exclusive. Is that true? An event and its complementary event are always mutually exclusive events. True? In other words, if event A is that a light bulb is on, and event B, the complementary event, is that the light bulb is off, are those mutually exclusive events if we check in on a light bulb during some random time? Are those mutually exclusive events?
Yes.
Yeah, because a light bulb, cannot be both on and off simultaneously in one instant in time. Okay, it's impossible. All right, so hopefully we're starting to better understand and get a feel for what it means for events to be mutually exclusive or not be mutually exclusive. All right, let's try number 3 here. Determine whether or not these events are mutually exclusive. 3A, drawing a card and getting a club or getting a 6. Are those events mutually exclusive? These two events here.
No,
No, because what card can we draw such that these events would occur simultaneously?
the 6 of clubs.
The 6 of clubs, correct? Those are not mutually exclusive events. Number B, 3B. Suppose we're rolling a die. Suppose event A is that we get a prime number, 2, 3, or 5, and event B is that we get an even number. Are these mutually exclusive events?
No.
No, because we could what? Roll a 2, which is both a prime number and what? An even number, correct? So those events could occur simultaneously. They are not mutually exclusive or they are not disjoint. All right, next one. C, rolling 2 dice. Is it possible to get a sum of 9 or get a sum of 12? In other words, are these two events mutually exclusive or not? Rolling a sum of 9 and rolling a sum of 12, are they mutually exclusive events?
Yes,
Yes. They cannot occur at the same time. When you roll 2 dice, there's no way that you can roll a sum of a 9 or a sum of 12 simultaneously. It's not happening. Those are mutually exclusive events. B, suppose our experiment is selecting a student at random. Event A is that we select a student that commutes to and from school. Event B is that we select a business major. Are these mutually exclusive events?
No.
No. No, because we could select a commuting student that is majoring in business, correct? So those events could occur simultaneously. Those are not mutually exclusive or disjoint events. All right. So is it more clear now what it means for events to be disjoint or mutually exclusive? All right. So for classwork number 1, I want you to do 4A through D. We'll call this classwork 1. Just determine if these two events are mutually exclusive or not. Go ahead and do those. All right, let's take a look at 4A here. The experiment is rolling 2 dice. And the first event is that we get a sum of 7, and the second event is that we roll doubles. What does it mean to roll doubles? Well, it means that the faces are what? Basically identical. Do you agree? Like you roll both dice and they come up both as like 2s. Okay. That's rolling doubles. So are these events mutually exclusive?
Yes.
Yeah. If you roll doubles, you cannot roll a sum of 7. Because 7 can only be obtained by rolling a what? How are all the ways we can get a 7 here? We could roll a what? A 1 and a 6, correct? We could roll a what? A 6 and a 1. We could roll a what? 2 and a 5. Or we could roll a 5 and a 2. Or we could roll a 3 and a 4. Or a what? 4 and a 3. And that's it, correct? Notice none of these are doubles, all right? So those are mutually exclusive events. You cannot roll doubles and a sum of 7 at the same time. What if I change this problem? What if I said the first event is getting a sum of 6 and rolling doubles? Is that possible at the same time? To roll doubles and get a sum of 6?
Yeah.
Yeah, you could roll what? A 3 and a 3, correct? All the 3s go like this. I think they're diagonal. Yeah. Yeah, you could roll a 3 and a 3, couldn't you? So it would be possible in that situation to have both events occur at the same time. All right, how about B, selecting a student in your college? The student is a sophomore is one event, and the student is a business major, the other event. Are these mutually exclusive events?
No.
No.
No, they could occur at the same time. You could select a sophomore that is majoring in business. So both those events could occur simultaneously. How about for C, selecting a course at random? The first event is that the course is a calculus course, and the second event is that it is an English course. Are those events mutually exclusive?
Yes.
Yes, you cannot select a course that is both a calculus and an English course simultaneously. At least I've never heard of such a thing. All right, how about D? Selecting a registered voter at random. The first event is that the registered voter is a Republican, and the second event is that the registered voter is a Democrat. Are these mutually exclusive events?
They're mutually exclusive.
Yes, they are. I mean, you can't be both 100% Republican and Democrat at the same time. I mean, you know, it's just not possible. Okay, mutually exclusive. Do we understand more clearly what it means for events to be mutually exclusive or disjoint? All right. Now here's an interesting problem. Number 5. College degrees awarded. The table below represents the college degrees awarded in a recent academic year by gender. Bachelor's degree, master's, and doctorate. Okay. Choose a degree at random. Suppose I randomly select a degree. Find the probability that it is a bachelor's degree. Well, how are we going to answer this question? Well, first of all, we're going to have to add up our columns. Okay, so we need to find out how many bachelor's degrees were awarded. So we're going to sum up our columns here. So adding up our columns. I get for the first one, that's a lot. I get 1,348,000 and 503. All right, what's the sum of the number of master's degrees that were awarded? 512,645 master's degrees, and the number of doctorates that were awarded. We're going to add this last column together. Then 6 and 4. Okay. Now out here at the end, we should have what's called the grand total. So we should add all these numbers together to give us a big old grand total there. 3 plus 12, 645 plus 46 is 024. And I get like 1.9 million. So I get like 1,907,772. All right, now how would we answer this question? If I randomly select one of these degrees, we're assuming that each one has an equal chance of being selected. What would be the probability of selecting a bachelor's degree? How do I compute this? I used the equal likelihood model we seen a couple of days ago, correct? So I'm going to divide what by what? The probability of selecting a bachelor's degree would be equal to what?
Both men and women getting bachelor's degrees, that total divided by the grand total.
You take the total number of bachelor's degrees awarded, which is 1,348,503, and we're going to divide this by the total number of degrees awarded by the institution. All right. 0.7172. All right, so we get on our calculator and dial it up. And what would we get for a decimal? Let's see. Do we get about 0.707?
Yeah.
Approximately about 0.707. And so in our minds, we know that to be about a 71% chance that if I randomly select one of these degrees, we will select a bachelor's degree. Okay. Make sense? All right. Any questions about that problem there? All right. Let me know when we all, does somebody still need to get this written down or accounted for? Because I have to erase it in order to move the page. All right, going once, going twice. We all have this accounted for here. Okay, let's get rid of it now. And let's move on. All right. Now, B, a doctorate or a degree awarded to a woman. So what's the probability of randomly selecting one of these degrees and it being a doctorate degree or a degree awarded to a woman. I have a question for you, ladies and gentlemen. Since we have an or probability, we need to ask ourselves, are these events mutually exclusive? Are these two events, selecting a doctorate degree and a woman, mutually exclusive?
No.
No, because we could select a woman that earned a doctorate degree, so they are not mutually exclusive. Because they're not mutually exclusive, will I use addition rule number 1 or 2?
2.
2. So this probability is going to be found by taking the probability that somebody earns a doctorate plus the probability that the degree selected belongs to a woman minus the degree, probability rather, that the degree selected is a doctorate degree and belongs to a woman. We got to use addition rule number 2. Okay, got to use that one. So what's the probability of select, son of a gun? I lost all my numbers. Really? I forgot about that. I thought this was just one question. All right, anyways, I lost all my totals down here. Does anybody have those maybe written down? I didn't write them down. I should have wrote them down. All right, what's the probability of selecting a degree and it being a doctorate degree? How many doctorate degrees were there? Does anybody have this number down here? This total down here?
It's 46,024.
46,024. Thank you. And then we're going to divide that by the grand total, the total number of degrees awarded, which I think was like 1.9 million something. 1 million, what was it?
1,907,172.
1,907,172. Okay. Plus the probability that we select a woman. Well, we got to add up how many women now. We need to do this row total here. We got to add up how many women we got here. So we got to add these numbers together in the second row. So let's do that. 424. 21, 683. All right, so there's 1,098,000 371 women. And then we're going to divide that by the total number of degrees that were awarded. So we take this number of women degrees that were issued and divide it by the total number of degrees awarded, which is 1,907,172. Then we're going to minus off the probability of selecting a degree that is a doctorate and belongs to a woman. So a doctorate and belongs to a woman, ladies and gentlemen, is going to be this number of degrees that were both a doctorate degree and issued to a woman. So this probability n, this joint probability, is going to be 21,683 divided by the grand total, which is, again, 1,907,172. Get on your calculator and dial this up, ladies and gentlemen, and you have the probability of selecting a doctorate or the degree issued to a woman. Okay, so we would have to actually dial it up on a calculator. Yeah, please don't leave it like that. I would like you to I would like you to report this as a decimal, and you can round it off to maybe 3 decimal places would be a nice place to round it off. Okay, the thousandths place. All right, let me know if anybody gets that. Let's see what they got here for the decimal. They got like 0.589. Anybody get something like that? No. 0.589. About a 59% chance of selecting a doctorate degree or a degree earned by a woman. Huh? Anybody get that?
Yeah, I got it.
All right. Okay. Well, that's a case where the events are not mutually exclusive. All right. All right. Okay. So do you see how we're doing these probability problems from this table where we have to, compute column totals or row totals to help us out and a grand total? All right. You have to do that with these tables to answer these questions here. What's the probability of selecting a doctorate degree awarded to a woman? Well, how many doctorate degrees were awarded to a woman? Seems like it would be that count, correct? So we would divide this by what? The grand total, which is 1,907,172. So if you take that and divide that by 1,907,172, you get the probability of selecting a doctorate degree that was awarded to a woman. Notice the way it's worded. You don't see the word or in here. So we interpret this as the probability that a doctorate degree, the probability that we select a doctorate degree and it was awarded to a woman. That's why we only take that 21,683 and divided by the grand total. That's it. And let's see what that is going to afford us. Anybody get it? About 0.011. Did anybody get that?
Yep.
0.011 about. All right, 0.011. So 1, 2, 1, 2. That's only like 1.1% chance. According to the numbers here. All right. What's the probability of selecting a degree that's not a master's degree? Not a master's degree. Now, you can do this problem a couple different ways. You can add up all the degrees that were not master's degrees, divide by 1,907,172, the grand total, or you could use the complementary probability rule. Another way to do this problem, to compute the probability of selecting a degree that's not a master's degree, is to say 1 minus the probability of the complementary event. And the complementary event would be that we select a degree that is a what?
Master.
A master's degree. See that, ladies and gentlemen? A little bit quicker, I think, if you maybe just use the complementary rule, because you only have to add up one column as opposed to 2 columns. A little quicker. Complementary probability rule. Because these events are complementary events. That's our complementary probability rule. Remember that rule? The probability of some event A occurring is always equal to 1 minus the probability of the complementary event A bar occurring. It's a complementary probability rule we've seen. All right, so to compute this here, we would like to know how many people earned a master's degree. And does anybody have that count there? Anybody write that down from previous problems? Well, we can add them up together again. That doesn't take too much. So that's the number of people that earn master's degrees. I'm going to divide this by 1,907,172. Then we're going to subtract that probability from 1. So 51,200, well, 512,000 rather. 645 divided by 1,907,172, which is about 0.268. And then we're going to subtract that from 1 to compute the probability of not selecting a master's degree. I'm going to call this 0.269. So the probability of not selecting a master's degree would be about 0.73, about a 73% chance. Okay. All right, so that's the probability of not selecting a master's degree. All righty, here's an interesting one here. Number 6. Do you guys want to try this one for a classwork problem, maybe? Or do you want me to work this one out? We can work it out as a class here. All right, the probability John will drive to school is 37.37. The probability he will ride with friends is 0.23. The probability that his parents will take him to school is 0.4. He is not allowed to have passengers in the car when he is driving. Notice. What is the probability that John will have company on the way to school? What is the probability that John will have company on the way to school? Well, how can that occur? To have company. He's not supposed to have anybody in his vehicle when he's driving. So how can that occur?
He's riding with somebody else.
Yeah, riding with somebody else. So this would be the probability then of either what? Ride with friends, or ride with what?
His parent.
Parents. Maybe have company then. Are these events mutually exclusive? To ride with friends or to ride with parents? Are those mutually exclusive events?
No.
Well, let's see. That's a good question. If he rides with his parents, it doesn't say anything about what? Not having some friends tag along, does it? Well, ladies and gentlemen, we have to assume that these are mutually exclusive because they don't give us the and probability or the joint probability of him riding with his parents and taking along some friends. We have to assume these are mutually exclusive. All right, so we will assume they are mutually exclusive. So therefore, how do we compute this or probability? It's going to be nothing more than the probability that we ride with what? Friends? Added to what? The probability that we ride with parents. So what is the probability that we ride with friends? Two, three. What's the probability we ride with our parents? Add these together. And there you go. So there's a 63% chance that we will have company when we go to school. We use the first addition rule because we assume these events are mutually exclusive. Okay. Everybody's got it there? All righty. That's all there is to that one. All right, we got that there? All right. Okay, now let's see what we got here. All right, ladies and gentlemen, number 7, the following doctors were observed on staff at a local hospital. Pathology, pediatrics, orthopedics. We have MD and we have doctor of osteopathy. All right. I would like you for classwork to try to do A and B here. Okay, so we'll call this classwork number 2. Classwork number 2, do A and B. All right. All right, let's take a look at these here. The probability that the doctor is selected as a pathologist. Let's see what we got here. Now, what you need to do here with this problem is you need to find the row and column totals for this table here, this data set. And you also need the grand total. So 38 doctors in total were surveyed. The probability that we randomly select one of these 38 doctors and the doctor being a pathologist. Well, how many doctors were pathologists? Well, that's going to be the sum of the first row. That would be 7 of them. And so 7 divided by 38 would be the probability of randomly selecting a doctor that is a pathologist. And it works out to be about 0.184. So there's about an 18% chance that we will randomly select a doctor that's a pathologist. Now, the probability of selecting a doctor that is an orthopedist or an MD, or suggests we're going to have to use an addition rule, but the rule we use depends upon whether or not the events are mutually exclusive or disjoint. Could these events occur at the same time? Could we select a doctor that's both an orthopedist and also an MD? Well, that's definitely possible, orthopedics and MD. So we have to use the general addition rule or addition rule number 2. That's going to be equal to the probability that the doctor is an orthopedic added to the probability that the doctor is an MD, subtracting off the probability that we select an orthopedic and that doctor also being an MD. So the probability of selecting a doctor that's an orthopedic, how many orthopedics do we have? We have 22. Sum of this last row, 22 divided by 38 is that probability. The probability of selecting an MD, how many MDs are there? There's 33. Divide that by 38 to compute the second probability, minus the probability of selecting an orthopedic and an MD. How many orthopedic MDs do we have? We have 20 of them. Orthopedic and MD, 20 divided by 38. Going through the arithmetic, we get 0.921, about a 92% chance. All right, is this making sense how we're computing probabilities from a table here? Okay. So we got that there. All right. Okay, let's see what else we got here. All right, you can also add this to your classwork number 8. Let's do number 8 also here, Liz. We'll just throw that into classwork number, whatever it is, 2, whatever. It's part of the classwork. Do number 8. All right, let's check these out here. Number 6, 8A, first of all, you want to have a total down here. The probability that we select a child and that child selected an athlete or a musician. Now, we have to assume that these are all mutually exclusive events here, because they don't give us any numbers for any possibilities of, you know, admiring both. All right. So the probability of selecting a child and the child having selected an athlete or a musician, we just add these individual probabilities together. So 11/60 plus 16/60 27/60 or 0.45. Did anybody get that for A? 0.45, 45% chance.
Yes.
For B, the probability of selecting the child and that child having selected a comedian or a politician. Again, we're assuming these are mutually exclusive events. Would be just the sum of the individual probabilities. So it'd just be 8/60 plus 3/60 11/60 or 0.18. Now the probability, did anybody get 0.18 for that one?
Yep.
Yep.
Probability we select a child that did not select an actor. You could do it the hard way, or the easier way is using the complementary probability rule, which is to say this probability is just equal to 1 minus the probability that the child should be child. 1 minus the probability that the child selected an actor. And so it'd be 1 minus 22 divided by 60, which is 0.633. Correct? Using the complementary probability rule is quicker than if you add 16, 11, 8, and 3 together. It takes more time. Why not just use the complementary rule? Anybody get 0.633?
Yep.
Yes.
Okay. All right, we good on that one? All right, another one I want you to do, part of your classwork. So we have a running total or an open tab on our classworks here. So number 12, try that one. This will be added to your classwork here. Go ahead and do that one there. Number 12. Little hint for this one, ladies and gentlemen, you want to try to construct a table, okay? That's going to help or expedite your ability to compute these probabilities. And I'll give you a hint. You could have 2 rows labeled how? Adult versus child, and the columns would be labeled what? What do you think? Adult versus child for the rows, and the columns would be
Fiction, nonfiction.
fiction versus nonfiction. There you go. That'll help immensely if you make a table. A table really helps here, and it really helps you to put this together more efficiently. So this is the table: adult, child, fiction, nonfiction, and I put the numbers in where they all belong, and I have some total column totals, row totals, and a grand total here. Probability of selecting a fiction book would be how many fiction books? 130 divided by 260.5. The probability of not selecting a child nonfiction book. You could do it the long way, which is not child nonfiction book, would mean you add 30, 70, and 100 together and then divide that sum by 260. Or you can use the complementary probability rule. This probability is really equal to 1 minus the probability of the complementary event, which would be that we do select the child nonfiction book. which will be 60 of them. 60 divided by 260. 1 minus 60 over 260 is really 200 over 260. Same thing, same answer, all right? Finally, the probability of selecting an adult book or a child nonfiction book, or suggest we use an addition rule, and these are mutually exclusive events in the sense that we're not going to select an adult book and a child nonfiction book simultaneously. So we just add the individual probabilities together. Probability of selecting an adult book would be 100 over 260, plus the probability of selecting a child nonfiction book would be 60 over 260. This is 160 over 260 or 0.615. Did anybody get any of those correct?
Yep.
Yep.
All right. Okay. Number 16, Liz Owen, go ahead and do that one there. This will be a part of your classwork also, number 16. Let's dial this one up. We already have a table kind of established for you. You're probably gonna have to get some row and column totals, so. Okay. This table here, you always want to try to, when you have a table, try to add up your values. So you want to have some column totals here and some row totals, and of course you have a grand total. This is the age column, less than or equal to 19, 20, and 21. Let me double check something real quick here. 20 or female. Oh, you know what? I did not do one of them. I'll work out the last one on the fly here, but all right. Let's look at A and B at least. A says they want to know if we randomly select one of these drivers, what's the probability that the driver is a male and less than or equal to 19 years of age? Well, how many males do we have that are less than or equal to 19 years old? That'd be 4,746 divided by the grand total. And that'd be about 0.301, about a 30% chance of selecting a male, and that male being no older than 19. Anybody get that?
Yes.
All right, now B is the probability of randomly selecting a driver, and that driver being age 20 or a female. Are these events mutually exclusive?
No.
No, we could select a 20-year-old female, so we have to use the what they call in your textbook the second addition rule, or the general addition rule. That's going to be found by this probability would be computed by adding together the individual probabilities and subtracting off the joint probability at the end. So the probability that we select somebody that's age 20, how many 20-year-olds we have? 3,178 divided by the grand total. Plus the probability of selecting a female. How many females do we have? 7,697 divided by the grand total. Minus what's the probability of selecting a 20-year-old female? 20 years old and a female would be 1,553 out of the grand total. You are looking at your final answer, which is 0.592. Did anybody get that? About a 59% chance.
Yes.
Randomly selecting a 20-year-old or a female, assuming that every one of these drivers has an equal chance of being selected. We're using the equal likelihood model to compute these probabilities. That's the key there. All right. All right. Now, part C, I did not do, but I just realized there is a part C, but I will work it out now amidst you. The probability of selecting at least a 20-year-old, at least a 20-year-old. Okay. Well, the probability of selecting at least a 20-year-old at least a 20-year-old. Do you agree? I could rewrite this as the probability of selecting a 20-year-old or a 21-year-old. Do we agree with that? That this probability is equal to this?
Yes.
Okay. And it's an OR probability. Are these events mutually exclusive? And the answer is obviously yes. You cannot be both 20 years old and 21-year-old simultaneously. So this is going to be equal to the probability that we randomly select a 20-year-old, just added to the probability that we select a 21-year-old. That's all there is to this probability. No, so what's the probability of selecting a 20-year-old? Well, there's 3,178 20-year-olds divided by the grand total. That's the probability there. Plus, what's the probability of selecting the 21-year-old? There being 3,306 of them divided by the grand total. And all we got to do is dial this up, and we got our answer. Okay, well, right there. So that's all you got to do is dial this up, 3,178, add it to 3,306. That's going to be 6,484 divided by 15,747. And when you do actually do the division on your calculator, I would like you to convert it into a decimal. We get about 0.412. I'm going to round it off to the thousands place, so this is approximate. Anybody get that for an answer?
Could we also do the complementary one where it's you take the total of the 19-year-olds?
That's right.
One
Another
minus
way
that.
Yeah, another way you could have done it is to say that this probability is really equal to 1 minus the probability of the complementary event. And the complementary event of saying somebody's at least 20 years old would be admitting that their age is what? Less than 20 years old, correct? That their age is less than 20 years old, which is to say 19 or younger. Yeah. So therefore, you could have said 1 minus the probability of having an age be less than 20 years old would be to say that their age is less than or equal to 19, and there are 9,263 of them, divided by the grand total, 15,747. And we should get the same answer. Do you agree? We should. Or else there's something wrong with the complementary probability rule. But I have faith in it. So, do we get the same answer? And the answer is what? Yes, we do. Okay. So you'll still get the 0.412 approximately. Yeah. Yeah, you can use the complementary rule. And that's nice to know and nice to see that you are latching on to that rule because that does save you in certain circumstances. That can save you a ton of time. You'll see, ladies and gentlemen, that this complementary probability rule comes in very handy when we start computing binomial probabilities later on in this course. It can be a huge time saver. Okay. All right. What time is it? 13 there. All right. One more problem. Let's see if you can maybe tackle number 22 and then we'll call it quits for the day. Okay. Now, for this one here, you might want to try to make a table because otherwise you're going to have these numbers swimming around in your head and it's going to be difficult to coherently put this together in your mind. So try to make a table. Now let's see. How would we label our columns and rows? Let's read it. It says, a recent study of 300 patients found that 100 alcoholic patients, that of 100 alcoholic patients, 87 had elevated cholesterol levels, and of 200 non-alcoholic patients, 43 had elevated cholesterol levels. If a patient is selected at random, find the probability the patient is the following. So what do you think our rows and columns could be labeled? Anybody? To give us a jump start here.
Alcoholic and non-alcoholic.
Yep,
patient.
alcoholic versus non-alcoholic versus the other labels would be what for the other ones, later the columns or the rows would be elevated cholesterol levels versus what? Non-elevated cholesterol levels. Do you agree? There you go. So I'll tell you what, let's have the rows be the alcoholic versus non-alcoholic patients. And the columns be the elevated versus non-elevated cholesterol. Okay, go ahead and do this problem here. Last classwork. All right, so here would be the results here. Probability of selecting a alcoholic with elevated cholesterol would be 87 over 300, which is that as a decimal. Probability of selecting a non-alcoholic would be 200 over 300, 67% chance of both. Probability of selecting a non-alcoholic with non-elevated cholesterol, non-alcoholic, non-elevated, 157 over 300. 0.523. We did not have to use any addition rule for any of those problems there. Okay, so did anybody get any of those?
Yep, you got them all.
All right, well, that's it, ladies and gentlemen. I covered the 2 addition rules today, and next week we'll get into some multiplication rules. You guys have a great weekend. I'll stay on the line if there's any other questions or comments. All right.
So I see that there is